seconds. So we have to look for the what is the magnitude of the force. Yes, we're looking for the force. So you have your initial velocity, you have your final velocity, and then you have your time, and then you have your mass as well. So remember that impulse is equals to force multiplied with any change in time if you have, which is equals to mass multiplied with change in velocity. So your force then will be equals to mass multiplied with change in velocity divided by if you have your change in time there. So this is equals to F is equals to now this mass here, you know, the mass is 100 grams. So if your mass is 100 grams, please you must always convert to SI units by dividing by 1000. So when you divide that one by 1000, 100 divided by 1000, that gives 0.1 kilogram. Are we together? So that means that your mass is 0.1. Your change in velocity, that is V final minus V initial divided by change in time. Are we still seeing the screen, please?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay, and this is equals to 0.1 into bracket. Now the V final, remember that our V final here is 10. That is moving in positive positive y axis. This is positive y. This one is moving in negative y. This one is moving in negative y. This one is moving in positive y. So which means that V final will be positive, that is 10. Then the normal minus that is there, which is this one. Now the V initial is going to take another negative minus 10. Okay? Because that one is moving in negative x axis divided by you have your 0.1 there, which is the time. The time is of course 0.1 seconds. So from here, this can cancel out this, and then 10 plus 10, you have that to be 20 Newton. Okay, so everybody got it right. So 20 is absolutely incorrect. All right, let's move quickly. So we have 20. So now conservation of momentum. Are we still together? Can you see the screen?
Yes, sir.
Yes, sir.
Yes, sir.
So conservation of momentum.
Yes, sir.
Okay, conservation of momentum will always be considered in an isolated and a closed system. So if you want to state the conservation, you might be asked in maybe probably your WAEC exam or something that states the principle of conservation of linear momentum. So you're going to begin with in an isolated or a closed system, the total momentum of the system remains constant in time. So when we are talking about an isolated system, it is a system whereby there are no external forces, and for a closed system, no mass enters or leaves the system. So linear momentum of each colliding body may change, but the total momentum of the system cannot change. That is, individual components. For example, now look at this one here. Individual components may have changing momentum, but in that system, you don't have like in the overall system. Let me put it that way. Okay, for example, when this one and this one collide together, this one is moving with a particular momentum, this one is also moving with a particular momentum. At a point whereby they collide, yes, there's a change in momentum for this one. There's also a change in momentum for this one as well. However, the overall momentum of the system does not change. Any. So conservation now. So you want to look at, uh, for example, look at this one. This blue one with mass m1 and velocity v1 moving towards this orange ball with velocity v2 and mass m2. This is moving in positive x-axis. This is moving in negative x-axis. Please, direction is very important as far as momentum is concerned. So to apply this To apply this impulse momentum theorem, you said the force of mass m1, sorry, the force of mass m2, this one, on m1, that's why we write f21 with delta t, is equals to mass 1, uh, let me see, sorry, this would be the force experienced by mass m1 due to the action of mass m2. Yeah, that should be the best way to put that. So that will be the, what's it called now? They change the momentum for this object, mass m1. So the change in momentum will be mass initial and then sorry, the mass one, that's the mass of the blue ball, multiply with the final velocity of the blue ball minus still the mass of the blue ball, that's m1, and the initial velocity of the blue ball. So what we just add here is just the change in linear momentum for the mass one, that's for the blue ball. Okay, and then this is this will be the first experienced by objects, or let me say ball 2, due to the action of ball 1 on it, or let me say the force exerted by ball 1 on ball 2. Yes, that is better. This force will be force exerted by ball 2 on ball 1. So force exerted by ball 1 on ball 2. So delta t, that's the impulse, will be equal to the change in momentum for this mass m2, that's m2 v2 final minus m2 v2 initial. Are we still following, please?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay, so one thing you need to take note that here, uh the force will actually be in opposite direction, because force exerted, force that this one will be able to exert on this one will be opposite, and of course because they are moving in opposite direction, so you expect that to be negatives of each other. So then you're able to, the f21, this is it, you bring it here, and then the f12, this is it, but it's going to have negative attached to the outside, this is it here. So you're eventually going to have that we rearrange by bringing all the initials together, or first we open these brackets with this negative sign. We have negative m2 v2 final minus, sorry, negative m2 v2 final plus, because this minus is going to multiply with this minus and it's going to change to plus, m2 v2 initial. So we rearrange. So when you rearrange, you want to take all initials to the left hand side and you want to have the all finals on the right hand side. So uh this is having initial, this is having initial. This one can go to meet that one because this will be plus here. So virtually everything will be plus on both sides. So positive, 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 positive on both sides. So this is the principle of conservation of momentum. That is M1. Let me use our normal symbols now, using U to represent initial velocities. So if I'm to use U, I mean letter U. If I'll be using letter U, if U is representing initial velocity, as the case may be for better understanding, and V represents final velocities for those objects. So that equation can be M1 U1 plus M2 U2. Those are all the initials. Okay, those are all the initials. You have, is this going to change? It's not changing. It's supposed to convert to the shape for me. Let me try that again. Okay, All right. This is M1. This is M2. Initial velocity 1. Initial velocity 2. Are we together? This moves
Yes, sir.
in this direction. This is moving in this direction. So those are in opposite directions. So now there will be collision here. Collision happens. Now the kind of collision that happens here will be divided into two cases. Maybe an inelastic collision. We are still going to see that shortly as we progress in the presentation, and maybe an elastic collision. What does it mean? Talking about inelastic collision, the two objects they move together. That is, if after collision you now have something like this. That is, if after collision you now have something like this. Oh, sorry, that doesn't give you better shape. If after collision you have something like this, uh, let's just manage that. Move together. In elastic, you have them moving separately. Maybe this then continue the other way, reverse, and then this continue the other way, the reverse. So in inelastic collision, you see them moving together. And in elastic, there's a rebound. This rebound in opposite direction, that rebound in opposite direction, that's elastic. So what is very important is that here, the kinetic energy is conserved. Here, kinetic energy is lost in the system. Are we still together?
Yes, sir.
Yes, sir.
Okay. So if I'm using u as initial velocity, you're going to have m1 u1 plus m2 u2 is equals to m1 v1 plus m2 v2. Just take that as your formula for conservation of linear momentum. So your job will now be to label your parameters. Is this one mass 1? Is this one mass 2? Is this one u1? Is this one u2? Is this one v1? Is this value v2? So if you're able to label those parameters, then solving the question will not be difficult. Okay. So now let's proceed. Let's continue. Uh, okay, I think we are done with this one. So conservation, yes, we've talked about that. So let's look at this very beautiful question. You have an anchor stand at rest on frictionless ice and fires a 0.5 kilogram arrow horizontally at 50 meters per second. The combined mass of the anchor and the bow, this whole thing here, is 60 kilograms. With what velocity does the anchor move across the ice after firing the arrow? Is that not a very beautiful question? Hmm? Hello, can we hear me?
Yes, it is.
Okay. So first thing first, we must be able to label the question, the parameters. So eventually you must know that your momentum must still conserved. So whether you're going to have your initial equals or the final. So yes, it's still all about conservation of linear momentum. Now, the mass one, I said first thing first, we want to be able to label mass one, mass two, u1, u2, v1, v2. So if you're able to do that successfully, then you shouldn't have a problem. Now, uh, here we label the M1 as 60 kilogram, and that M1 is the combined mass of the anchor and the bow. Okay, and M2 is 0.5 kilogram, which is the arrow itself. Okay, so the arrow is what we are, of course, uh, firing forward, and then the anchor and the bow has its own mass to be 60 kilograms. So what's it called now? The initial velocity, where is it? Initial velocity of this mass m1, that's the Aka and the bow. It's definitely not moving it's at rest. Why? Because it's just at this stationary point. There's no motion at this point here. The person is just standing, so the Aka and the bow are remaining in that same position. And also the arrow too, initially is at rest because it's still held in this person's hand, as you can see here. The person is just holding. It hasn't fired it. The person hasn't fired the arrow forward. Now, as it releases the arrow, is going to have a particular velocity. He said fires a 0.5 kilogram arrow horizontally at 50. At 50, that's the what's it called now? Velocity of the arrow. Are we together? That will be the velocity of the arrow. So if I label the arrow to be 2, then that means that V2 final of that arrow will be 50. So we are now looking for uh, the V1 final for the Aka and the bow. That's what we are looking for. Do we get this interpretation, or I need to run over it again? Hello, can you hear me? Ah,
So I can explain it again.
okay. How about others? Are they asleep? They've all slept.
So I explain it again.
Yes, yes. Let's go over it again. I know it will be confusing, kind of. So, um, this whole setup here, this whole thing with together with this place, that's the Aka and the bow. The Aka, the bow, holding this arrow here, about to fire. Now, the Aka and the bow together with the arrow, they are all at rest. They don't have any initial velocity at all. So you now want to label which one is 1, which one is 2, which one do you want to give M1, which one do you want to give M2. Once you've been able to assign that 1 and 2, you shouldn't make the mistake of their velocities as well. U1 should be for 1, U2 should be for 2, V1 should be for object 1, and V2 should also be for object 2. So here now, okay, based on this solution now, we've assigned M1 to be 60. That is, we take the Aka and the bow as the first object, that's M1. If you were the one that wants to solve, you may actually decide to use this one as mass 1. It all depends. So which means that if you label this one as mass 1, this one will be your what? Your final velocity 1. Final velocity 1. Remember they said that at rest, that means initially, they all have initial velocity to be 0. But at the point whereby we now fire the arrow, whereby it has now moved, it has moved away from rest. It has attained this velocity of 50 meters per second. That's the final velocity of the arrow. So the mass still remains 0.5. This is the final velocity of the arrow. The initial velocity of the arrow will be what? 0. So the combined mass of the Aka and the arrow and the bow is 60 kilograms. This is another mass. Another mass. Let me try to solve again. Let's show that on the whiteboard. So suppose you are the one that want to solve now. Because you are meeting the 0.5 kilogram first, you may decide to call it mass 1. Are we together? Now, since they've mentioned that they were both at rest before, then that means that the arrow 1 is equals to arrow. The arrow was at rest, so its initial velocity is 0. Mass 2, which is the Aka, its own mass is 60 kilograms. It was also at rest at that time. That's zero. Now, as soon as we fire that arrow, the arrow attained a final velocity. That's v1 for for the arrow now. It attained a final velocity of, what is the final velocity again? Is that 50? Okay, that is 50. 50, 50 meters per second. And for this one, this is what we are looking for. It's actually very straightforward. What you just want to do is, I want to, whenever you have this something like this, you have in mass one, you have in u1, you have in mass two, you have u2, you have v1, and you want to look for v2. Just put it into conservation of linear momentum. Linear momentum will be conserved as long as it's a closed system. So using m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. Okay, so here now m1 is 0.5 multiply with u1 0 plus m2 60 plus u2. U2 is what? 0, right? Oh, sorry, not plus. That's meant to be multiplied. Sorry, multiplied by 0 is equals to our m1 is 0.5. What's our v1 there? Our v1 is 50, right? Plus m2. M2, that's the aka and the bow, that's 60. And then we're looking for v2. Okay, are we still together? Are we still together?
Yes, sir.
Yes, sir.
This implies that all the initial momentum, all what you are going to have on this side, it is what? 0. Is equals to 50 multiplied with this, that's 25 plus 60 v2. For me, you are going to have that 60 v2 is equals to negative 25, and then v2 equals to negative 25 divided by 60. What are we going to have there? Negative 25 divided by 60. What's the answer to that?
It's 0.42.
Is 0.1? Negative. Negative is there, please. So who can tell me why do we have it to be negative? It's basically going to have it as negative. Why? We're going to have it as negative because according to Newton's law of motion, that's the third law now. The third law states to you that for every action, there is always an equal but opposite reaction. So yes, if the archer is shooting or is firing an arrow going forward, yes, it's going to have an effect. And the effect is that once this one go forward, yes, you expect the archer and the bow to experience a something like a rebound effect. Like they're going to go shift, like adjust backward a bit. It's just a normal effect that will happen. It's just like firing of a gun as well. When you fire a gun, once the bullet has been ejected, from the mouth of the pistol, it's going to have a rebound effect. So the action is the bullet coming out of the pistol. The effect is the rebound that the person that shoots, you know, the person also, kind of uh experience the effect. So there's an effect. So that is why we have this velocity to be negative here. Okay. So that's about the aka and the bow. So we have that. So see under conservation of linear momentum, we have a 100 kilogram man and a 50 kilogram man on ice skates stand facing each other. If the woman pushes the man backwards so that his final speed is 1, at what speed Does she record? Yes, we usually, that thing that I was trying to mention, whether the actor and the bow and the arrow, or maybe firing a gun and the person holding the gun, we call it recoil. So what you're looking for is recoil velocity and all of that. Do you get what I'm trying to say?
Yes, sir. Yes, sir.
Yes, sir.
Okay. So do you all want to try this, or we should look into it together? Let's look into it together, not to take too much of our time. So the question, you have 100 kilogram man and 50 kilogram man on ice. They are standing facing each other. Standing facing each other. So you have this one and then this one. Let's say this is the man here. Let's say this is the woman here. Okay. If the woman pushes the man backward so that his final velocity is, you can see, if they are standing there, that means that their initial velocity was 0. So you are basically going to say initial velocity. Let me take this one as 2. So that means this one you expect mass 2 there. If I take that one to be 2, of course there must be 1. This will be 1. Initial velocity is what? We don't know. So initial velocity is 0 because they are standing. Is 0. So what is mass 1? Mass 1 is for the man, and the man is 100 kilogram. 100 kilogram. The woman is 50. Is that 50? Okay, that is 50. 50 kilogram. So it was now said that this woman pushes this one so that this has a backward velocity. That will be the final now, right? Final is equals to what? We mentioned that 1 meters per second. So what will be the recoil of the woman? We're looking for V2. Are we together? Do we get the
Yes,
question?
sir.
Okay. So now I want to solve. Basically, you are still going to use your conservation of linear momentum. M1 U1 plus M2 U2 is equals to M1 V1 plus M2 V2. So since they are standing at each other, they don't have any what's it called initial momentum because their U1 and U2 are 0. So this one will be 0 plus 0. When you multiply, you gives you 0. Now M1 mass 1 is 100. Final velocity of the man. Now they said it moves backward, right? Yes, backward was mentioned there. So it's moving in negative what? X axis. So because it is moving in negative x axis, what am I going to do? I'm going to attach negative 1 there. Plus M2. M2 is what? 50. And then V2, that is what you are looking for. So which implies you're going to have 0 is equals to negative 100 plus 50 V2. Take the negative 100 to that side. You're going to have 100 is equals to 50 V2. And then divide both sides by 50. Divide both sides by 50. You're going to have V2 is equals to 100 divided by 50, which is equals to 2 meters per second. Does it make sense?
Yes, sir.
Who can tell me why is it positive? Can anybody say why it is positive? It's just like you facing someone and then you try to push the person. Yes, you are going forward now. You are not going backward. It's the person that feel the effect. You are the action. So because you are going forward, you are in the positive x axis. It's the person that goes in the negative x axis. So it does make sense. So that is option E to that. What's the time now? Oh, 10:27. Are we okay? Alright, so let's move quickly. We don't have much time anymore. So these are types of collisions we have. All right, we've talked about this one. So types of collisions, momentum is conserved in any collision. It is important to note that whether you're talking about elastic or inelastic collision. Leave out the actual collisions. We actually have just elastic and inelastic for you to know. So in inelastic collision, you have the example rubber ball and hard ball. So usually in inelastic collision, I've mentioned that kinetic energy is not conserved. There's kinetic energy lost. Energy is lost. Okay, and the energy that is lost is because the initial kinetic energy is usually more than the final kinetic energy. So there will be a difference. When you subtract, you have a value. But in elastic collision, you always have both momentum and kinetic energy are conserved, meaning that kinetic energy before is equal to kinetic energy after. You can also have perfectly inelastic collision occur when objects stick together. Yes, when they stick together, it's said to you that it is a perfectly elastic. There is energy lost. So collisions summary, that's about that. Uh yes, that's collision summary. In elastic collision, both momentum and kinetic energy are conserved. In non-perfect elastic, momentum is conserved, but kinetic energy is not. Moreover, the objects do not stick together. That is a non-perfect inelastic collision now. So this points to you that inelastic collision may be two. There is the non-perfect and there is the perfect. In the perfect, they stick together. In the non-perfect, they do not stick together. Okay, but in those two cases, kinetic energy is not conserved. So in a perfectly inelastic collision, momentum is conserved, kinetic energy is not, and the two objects stick together after the collision. So their final velocities are the same. Yes, we are still going to look at that shortly. Elastic and perfectly inelastic collision are limiting cases. Actual collision falls in between most actual collision falls in between these two types. Yes, that's what you should know. Elastic, inelastic. So momentum is conserved in all collisions. Now, you need to know more about perfectly inelastic collisions. You should know that when two objects stick together after collision, they have undergone a perfectly inelastic collision. When they stick together, as you say here, this one collide with this one. This one mass M1 collide with mass M2. And then after collision, you now see something like this. It is telling you that they are perfectly what? Inelastic. And these ones that are moving together, they are going to be in they are going to have a common velocity. There will be a common velocity because they'll be moving together with a common velocity. And the summation of the mass here, or the overall mass of this combination or of this collision will be M1, that's mass 1 plus mass 2. So you're still going to apply the principle of conservation of linear momentum. Since you have that, let's quickly look at the principle of linear momentum on the board uh, for a perfectly inelastic collision now. Are we still together?
Yes, sir.
Oh, we already have
Yes, sir.
a rough edge. Okay. Ah, sorry. I didn't know it's not forming a perfect cycle for us. It should now. Okay, maybe we'll manage it like that. Ah, there is not a perfect object. Anyways, oh, we need to refresh. Am I having network issue again? Can we hear me?
Sir.
Are we are tired, Abby? Yes, we've already done. Yeah, we've finished collision, so we are moving to explaining perfectly elastic and inelastic collision. So um, Okay, so let's do it this way. Someone should screenshot this question for me and send to the group. Anybody doing that?